Take a brief look at example 19.8 in the textbook. And here we're going to try and determine the Q point of this transistor. That's to say, what is the collector current and what is the voltage collector to emitter in this circuit. As always, of course, we start from the base side. And we'd immediately come along and say, well, we just apply the voltage divider rule here to find the voltage at the base. And we can generally do that because the base current is quite small and can be assumed in many cases to be zero. Now, for that assumption to be true, we require that beta times Re must be greater than 10 times this resistor here, R2. And the reason for that is because if this impedance across here is about 10 times greater, then we can ignore it. However, in this particular example, the beta is given to us as 50. And so now we notice that beta times Re is equal to 50 times 1.1 K is equal to 55 K ohms. And this resistor over here, R2, is only 10 K. So since 55 K is less than 10 times R2, we must take the transistor base impedance into account. So we have to do that. And there's a couple of ways you could do that. Of course, the simplest way is just simply look up the appropriate formula in the textbook someplace and apply it. The textbook points out that the collector current under this condition, IC, is equal to some voltage V Thevenin minus voltage base to emitter divided by resistance Thevenin divided by beta plus Re. Well, if we knew those values, we could plug them in easily. We know what voltage base emitter is, we know what Re is, but what is this voltage Thevenin and resistance Thevenin? Well, what these are the values that the transistor sees looking back this way at the input source. So we're going to just redraw this circuit and Thévenize it. So if we do that, we can draw this as an equivalent circuit where we have a Thévenized voltage, which we will calculate, some Thévenized resistance, and then comes the transistor with its emitter resistor. So how do we apply this circuit? How do we calculate these values? Well, the Thévenized voltage is the voltage that we would see looking back this way if we disconnect the transistor. So the voltage Thevenin, in fact, is just simply the voltage divider rule. That's to say, in this case, 20 volts times 10K over 68K plus 10K. And that number just turns out to be 2.56 volts. And the Thevenin resistance is the impedance looking this way. And what we see here is just simply a resistor which goes from AC ground, a resistor which goes to AC ground, and it's simply R1 in parallel with R2. So that means that we take the product of this over the sum. So 10K times 68K divided by 10K plus 68K is equal to 8.72 K ohms. So that's the Thevenin circuit. So where do we go from that? Well, now we can apply our basic circuit analysis techniques we've been using all along to in fact derive this equation. So I want to show you that this equation actually can be developed, but if you happen to have it handy, well, that's fine, use it. So we're going to draw a current flowing in this circuit over here, and we're going to write Kirchhoff's voltage law around the base emitter loop. So starting from this point over here, we're going to see minus voltage Thevenin plus IB times the resistance Thevenin plus voltage base to emitter plus, and of course here we're going to have IC times RE, but IE times RE, but remember that IE is actually beta plus 1 times IB. So we'll just write that in right away, beta plus 1 IB times RE. Now what we're going to do is we're going to collect the base terms over to the left-hand side. IB R Thevenin plus beta plus 1 times IB RE is equal to voltage Thevenin minus voltage base to emitter. We can pull out the IB and we'll get resistance Thevenin plus beta plus 1 times RE equals to the Thevenin voltage minus voltage base to emitter. And then of course we can divide the left-hand side by everything in the brackets just to give us the base current. So we have now IB is equal to voltage Thevenin minus voltage base to emitter divided by resistance Thevenin plus beta plus 1 times RE. Now, of course, we're not really interested in the base current. What we're really interested in is in the emitter current, or collector current. So at this point, we can recognize that IB times beta is simply equal to IC. So if we multiply both sides of this expression by beta, we will get the collector current. So we'll do that. We'll multiply this by beta, so that automatically gives us IC. Multiply this side by beta, we'll get voltage Thevenin minus voltage base to emitter divided by resistance Thevenin plus beta plus 1 times RE, and the whole thing times beta. And that would give us the exact value. But of course, this equation doesn't look exactly like this equation. Not yet, anyways. So here we're going to do some simplifications. We'll say simply that since beta plus 1 is approximately equal to beta, we can rewrite this right-hand expression like this. Voltage Thevenin minus voltage base to emitter divided by resistance Thevenin plus beta times RE, and then the whole thing times beta. Now, what we can do is we can multiply both the numerator and the denominator by 1 over beta. And notice what happens. Collector current becomes this times beta times 1 over beta, so that beta disappears. This times 1 over beta, so there's a beta underneath. This times 1 over beta, so that beta disappears. And we end up with voltage Thevenin minus voltage base to emitter divided by the Thevenin resistance divided by beta plus RE. And here is the expression that you find in most textbooks describing the collector current if the beta on the transistor is too low or the resistor in the emitter path is too low to allow us to ignore the loading effects of the transistor on the voltage bias circuit. So now we can put it all together. We can now say that the collector current in our circuit is equal to the Thevenin voltage, which we've already calculated at 2.56 volts, minus the voltage base to emitter, which is 0.7 volts, divided by the Thevenin resistance, which we've already calculated at 8.72 k ohms, divided by beta, which was given to us, and that's 50, plus the emitter resistor, which is 1.1 k. And this number, the collector current, turns out to be 1.46 milliamps. Now from here, we can find the voltage across the collector to emitter very simply. Voltage from collector to emitter, applying Kirchhoff's voltage law again, is going to be 20 minus the collector current, 1.46 milliamps, times the collector resistor, which is 6.2 k, plus the emitter resistor, which is 1.1 k. And this turns out simply to be 9.34 volts, voltage collector to emitter. So we're done.